Okay, hey Jen, I'm gonna try to do my best to explain this decently. How does this look? Okay, sweet. So, we're first gonna look at the harmonic P series. I'm just gonna skip over this stuff because I feel like you'd have done it in Specialist, but I'm happy to go back and explain everything else as well if you want me to, so just send me a message. So I'll do a quick video explaining this slide because it's the whole basis of everything. And then I'll do another video going through a few examples using the knowledge from this slide. So first off, essentially the harmonic P series is just this, and if you break it down, you're just adding up a bunch of terms, right? So this sentence here is what we're going to deconstruct, and we're basically looking at why does it converge if P is greater than 1 and diverge if P is less than or equal to 1. So I think it's easiest to start off with P equals 1 because that's kind of the midpoint between the two bounds. And then we can look at what happens on either side of it. So for P equals 1, it looks like 1 over 1 plus 1 over 2 plus 1 over 3 plus. And then it continues, right? Because all we're doing is writing 1 over n, where n starts as 1. Now, the way that you can prove that this diverges, which essentially means it tends to infinity as the series goes on, is if we break it down into smaller chunks. So obviously 1 over 1 is just 1. 1 over 2 is just 1 over 2. Now, for this section here, instead of saying 1 over 3 plus 1 over 4, because you get some weird, 7 over 12, you can change the 1 over 3 to be something smaller. So let's say this is 1 over 4 plus 1 over 4 instead, right? Which gives us 2 over 4, which is just 1 over 2. And let's do the same thing for these next 4. Instead of having 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8, if we just change all of these to being 1 over 8, because we know they're smaller than the original terms, smaller than or equal to, 4/8 added up is 4 over 8, which is also 1 over 2, right? So essentially we start off with our original terms here, and we want to try change them and find an equivalent, like the ones above, which give us these countable halves, alright, because they're much easier to keep track of. Now obviously you start off with 1 term, and then 2 terms, and then 4 terms, and then you can imagine the next one's going to be 8 terms. But, as long as you have enough terms, you can keep making these halves, and these halves keep adding up. So you get 1, and then 1.5, and then 2, and then 2.5, etc. And so even though it happens really slowly, as the series goes to infinity, the sum is going to go to infinity as well, which means it's going to diverge. So hopefully that makes sense. Now, if you compare this to if P is greater than 1, let me just take this and wipe it out. The lecturers actually use some kind of software that shows it, which is quite a good visualization if you still don't get this. But let's just say P is 2, just to make it easy to count. You get 1 over n squared. So 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 5 plus 1 over 36. And I'll just do etc. because obviously it keeps going until infinity, and I can write fast but not that fast. So yeah. Now you can see already this immediately goes a lot smaller. And so where you got 8 terms before you reached 1 over 8 in the other series, now you've already reached it on your 3rd term. So even though you start off with 1 and then 1/4, which is still decently large, 1/9 is really small, 1/16 is really, really small, and soon these terms become really insignificant in terms of how much they're actually adding on. Which essentially means, if you look at the grand scheme of things, you'll start off with, if you start like here, it'll be 1, and then it'll be 1 1/4, and then it'll be 1 1/9, 1 1/16, and it basically flattens out completely. And that's saying it converges to a specific value. And because you can't make those same halves here, even though you have infinite terms, they get small so quickly that we can say it converges. Because essentially the amount that's being added reaches 0 very quickly. And the way to judge that is you can say that the limit of whatever function here as n tends to infinity, it tends to 0. So the only difference though is obviously if you do this also ends up as 0, but in our case that actually is considered as diverging because it doesn't end up as 0 quickly enough. So you have to be a little bit careful with how you explain it. They don't actually do a rigorous proof or anything in the lectures, so I'm not gonna do one here because it's not necessary. But it's just good to have some sort of intuition behind this sentence instead of just memorizing the value. And then finally, if you want to look at when p is less than 1, for the other diverge situation, let's say it's 1/2, so it's going to be 1/√n. Then you get 1/1 plus 1/√2 plus 3 plus 1/√4 plus da. Now, obviously you can do various different explanations, but the easiest way to say this is essentially we know that 1/√2 is going to be bigger than 1/2, and so because √2 is smaller than 2, and so you could change this to be the other series, and you can say that for every term, right? You can change this to be the other series we originally had, and then from there change that to be what we changed the other one to. And you can do that for anything where p is less than 1, right? You can say the denominator is smaller than when p equals 1, and therefore the term itself is bigger. And so you can keep showing that it goes to this series down here, and this tends to infinity, therefore the original one must tend to infinity, and therefore diverges. So hopefully it's a decent explanation for you. And just before I finish, I did see there are actually a couple slides down below, so I'll brush over those as well before I get to the example video. So yeah, like it says down here, all you really have to do is look at the exponent here. So this is a 1, right, obviously, and so therefore it falls into the p is less than or equals to 1, which means it diverges. This is a 2, which means it's p is greater than 1, which means it converges. So it's essentially just comparing it to what the original formulas are. Okay, I split up the video because I realized my explanation for this slide was absolutely stuffed, so I'm just going to go over it again. Essentially, this is all pretty intuitive. If you don't know this notation, I'll just read through it. So it's saying let an be a series and bn be a series, and c be a constant that's a real number but not 0. I only actually learned this the other day in a tutorial, so it's quite cool. And it's saying if both of these series an and bn converge, then the addition of them also converges, which makes sense because if you think of it, like an goes like this and converges at this line, let's say bn goes like, I don't know, like this, converges at this line. When you add them up, you're just going to get something up here or something, right? You're not going to explode anywhere. And same for the constant. If you multiply by c, as they say here, all you're doing is jumping it up or down by a certain amount, multiplying, let's say this is at 2 and c equals 3, then you just go up to 6. you're not going anywhere crazy because it's a constant. And similarly, if it diverges, that means it goes up to infinity. So it'll look like this, and it'll just keep exploding. If you multiply that by a constant, all you actually do is change the speed at which it explodes, right? So it's either going to look like that or that. At the end of the day, it's still going to explode up to infinity, and therefore it's still going to diverge. So that's pretty simple. The divergence test is you take the limit of whatever the function is inside the series, an, and if it doesn't equal 0, then that series diverges. Now, the important thing to note with this is that if it does equal 0, that doesn't mean it converges. So it's not that it goes either way, converging or diverging. It just means that it goes to diverging if it doesn't equal 0. And it says that here. If it does equal 0, then it may converge or diverge. It doesn't say it specifically does one or the other. And this includes the case that it doesn't exist as well. So if you find the limit d and e, it explodes to infinity either way. So let's say, I don't know, like something like this, where it's unbounded, and so therefore it does not exist. You can say that the series diverges. But if it does equal 0, then you need to use a different test, and we'll go into that a bit more later. I figured the way I'll actually split it is I'll go through this one example, because this uses the divergence test, and then I'll go through the rest of it in a separate video. So let's apply this knowledge to this. Does the series converge? So first we'll just take the limit, like it says up here, of whatever's on the inside. So limit as n approaches infinity of n plus 1 over n equals the limit as n approaches infinity of 1 plus 1 over n, because this just becomes n over n plus 1 over n, right? If you break up the fraction. And this is equivalent to 1 plus limit as n approaches infinity of 1 over n by limit laws. And that's just 1 plus 0 by standard limits. And that's 1, and that's not 0, which is the most important part. And since that's not 0, therefore what was it, n plus 1 over n. Actually, gotta be careful with wording here. It asks if it converges. So instead of saying it diverges, we just say it does not. And then specify that you figured it out by divergence test. So it's pretty simple to work out once you know the steps you're supposed to use. You might also even throw in a line of working at the start, somewhere here, basically just saying that like you're doing the divergence test, and then showing it. That probably would have been better. But yeah, I think that's basically it in terms of the divergence test. It's a pretty simple application. And yeah, we end up finding that it does not converge because it doesn't equal 0. Now I'll go into the comparison test in the next video. See you.